We're now going to derive a tangent plane equation and one that uses partial derivatives. So this tangent plane equation can be written in this form where we have it solved for z minus z naught, and we're using these two first partial derivatives as multipliers on our x minus x naught and y minus y naught factors. So let's recall what we already know about plane equations, which is that if we have an ordered triple that's a point in the plane, and a normal vector that is perpendicular to the plane, where the normal vector's components are a, b, and c, then the plane equation can be written as a times x minus x naught plus b times y minus y naught plus c times z minus z naught, and all of this is added up to be 0. So the formula that we're deriving is solved for z minus z naught, so that is a good place for us to start. To solve for z minus z naught, we'll simply subtract a times x minus x naught and b times y minus y naught from both sides, and then divide both sides by c. So now we have z minus z naught is equal to negative a over c times x minus x naught minus b over c times y minus y naught. Now we'll come back to this equation in a moment. Let's consider some arbitrary surface. Z is equal to some function of x and y, and we have our surface function drawn as if it's a sphere. And we're looking to find a formula for the equation of a plane that's tangent to this surface. So we'll pick some ordered triple on the surface that comes from the domain element x naught, y naught, and if we're in the floor, we'll actually say that the z coordinate here is equal to 0. So the ordered triple then that's on the surface is going to be x naught, y naught, and then the function evaluated at x naught, y naught as the z coordinate. Now, because we're trying to derive a formula for this tangent plane that involves the partial derivatives, we're going to take this surface and slice it with the constant plane that x is equal to x naught, some constant x value. When we slice with a constant x plane, we get this curve of intersection between the surface and the plane. Now at this ordered triple, we're also going to have a line that is tangent to that curve of intersection at that point, and we'll call this line L1. Let's notice that the slope of the tangent line that is L1 is going to be equal to the partial derivative with respect to y because x is being held constant, and that domain element x naught, y naught would be plugged into that first partial formula in order to give us the slope of this line. So let's just make a note that this is the slope of the tangent line for L1. So back up here to the drawing, let's do this again, but this time we'll slice with a constant y plane. So y is being held constant, and we're going to generate an intersection curve with our surface at this point. And again, our slicing plane is y is equal to y naught. So here is the curve of intersection between the slicing plane and the surface. And this curve has a tangent line at this point. We'll call this one L2. Now let's notice again that because we sliced with a constant y plane, the slope of line L2 is the first partial derivative with respect to x evaluated at x naught, y naught, that domain element. And so we'll bring that information down here as well. We'll be using it again in a moment. Now when we take this constant y is equal to y plane and intersect it with the surface, that's when we come up with this intersection curve C. But if we were to take this y is equal to y plane and fly on up to intersect with the plane, the line L2 is the intersection curve or intersection line between the plane y is equal to y naught and the tangent plane. So if we wanted to try to find the equation for this line, what we could do is take y is equal to y naught and plug it into what we have for the tangent plane equation. So let's recall from the beginning that we had z minus z naught is equal to a divided by c times x minus x naught minus b over c times y minus y naught. So let's get the equation of line 1 first, and in order to do that, we will take the slicing plane, which in that case was x is equal to x naught, and intersect it or plug it into the equation of the tangent plane. That gives me the line of intersection between the two planes. So when we plug this into the tangent plane equation, we get z minus z naught is equal to negative a over c. Plugging x naught in for this x gives me 0 in this position, minus b over c times y minus y naught. which then simplifies to being z minus z naught is equal to negative b over c times y minus y naught. Now x is equal to x naught, a slicing plane, is parallel to the YZ plane, and this is the two-dimensional equation of a line in the YZ plane, where the slope of that line would be negative b over c. But we also know that the slope of that tangent line was the first partial with respect to y, evaluated at x naught, y naught. So we're going to substitute that first partial in for negative b over c in just a moment. But before we do that, let's get the equation for line 2. Remember, line 2 is the intersection between the tangent plane and the plane y is equal to y naught. The two planes intersect in a line. So to get the equation of that line, we'll simply plug y is equal to y naught in for our y value. And when we do that, we get negative a over c times x minus x naught minus b over c. When y is y naught, this value is 0 here. Then we simplify down to getting z minus z naught is equal to negative a over c times x minus x naught. And this is again a two-dimensional equation of a line, but this time in a plane that's parallel to the xz plane. And the y is equal to y naught plane is a plane parallel to the xz plane. So this is that 2D equation for a line where the slope of that line is going to be negative a over c. But as we saw a moment ago, the slope of the tangent line 2 was the first partial with respect to x. So while that slope is negative a over c, it's also the first partial with respect to x evaluated at x naught, y naught, and then we can use this first partial as a substitution for negative a over c. So then our tangent plane equation then becomes, instead of a over c, we're going to plug in first partial with respect to x times x minus x naught. And instead of negative b over c, we're going to substitute first partial with respect to y, evaluated at x naught, y naught, times y minus y naught. And this is the equation of the tangent plane that we were trying to derive, one that uses these two first partial derivatives.